Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll be going through this June 2015. This is paper 1-1. So these are getting into all the syllabus where some of the questions in all the syllabus will no longer be available and will no longer be asked as part of the new syllabus. So always check your curriculum, your specifications. This is for the 9701 Cambridge International A-Level, but any of the contents covered within are entirely suitable for any 16 to 18 years old chemistry students around the world. In this first question, we have a Boltzmann distribution. So it shows the distribution of energy. These are the number of molecules and these are the energy for that particular number of molecules. And we have this particular line here called activation energy, which is the minimum energy that reacting particle must have before they can react or before they can undergo reaction. When you use a catalyst, how is the graph going to change? How is the Boltzmann distribution going to change when you use a catalyst? When I use a catalyst, I'm going to add in a catalyst activation energy here. So this is going to be a new lower activation energy as a result of an optional pathway with an overall new and lower activation energy. In doing so, I get an additional area, the red color one, in addition to this blue color one, which was the proportional effective collision from before, plus a new greater proportional effective collision when I use a catalyst, and that is why my reaction will be faster because I get a greater proportion of effective collision. But the height of the peak, the rest of the graph will remain the same. You don't change it, as only temperature can change energy distribution. The use of a catalyst doesn't do that, therefore the graph looks exactly the same. But the activation energy, which is new and lower, will move to the left as you have a new lower activation energy. D is the answer there. Number 2, which one is the best indication of the relative strength of hydrogen bond? Now the hydrogen bond is an intermolecular forces, so you are not breaking covalent bond. That is the first thing you need to think about. Intermolecular forces mean between the molecules, so that means we are not breaking the covalent bond between the atoms, not between the atoms. So this kind of questions always try and trick you with the covalent bond energy or bond dissociation energy or bond enthalpy. So got nothing to do with this bond dissociation energy because we are not breaking covalent bond. So what are we doing here? We are trying to look at hydrogen halide in terms of the formation. So H2 gas plus the halogen, which could be solid, liquid or gas depending on if you have iodine or bromine or fluorine or chlorine, and then you're going to get HX. Actually, you're going to get 1 mole of HX because it's enthalpy of formation. So forming 1 mole of the substance from its element in their standard state. This is gaseous there. Okay. Again, you are breaking the covalent bonds and you're forming a covalent bond, so it's got nothing to do with B there. Enthalpy changes of solution, so you're just dissolving the gaseous hydrogen halide, dissolving a large amount of water, and you get HX aqueous. Or the last one is vaporization, so HX liquid going to HX gas. These are simple covalent molecule and they have simple covalent structures, so that means you are just breaking the weak intermolecular forces of attraction as you try to melt or boil in this case. Vaporization is the same as boiling, so they don't call it enthalpy change or boiling because it sounds strange, but vaporization is liquid going to gas, and these are simple covalent molecules. Definitely we are breaking the weak intermolecular forces of attraction between the molecules, and definitely for the case of hydrogen halides, in terms of hydrogen fluoride, HF will have hydrogen bond between the molecules, and therefore they will tell you how much energy is required to turn the liquid into gas. They will tell you the strength of the hydrogen bond there. Number 3, we need the data booklet relevant to this question. So I have a feeling that this is just using the periodic table. So let's have a look at this question. 1 gram of carbon is combusted in a limited supply of pure oxygen. If you have limited supply, you don't get complete combustion, and therefore not all the carbon forms CO2. You get some formation of carbon monoxide, which is actually a toxic gas, and it can kill you as a result of its toxicity. Now this resultant mixture is passed through excess NaOH. NaOH is a base, is an alkali, so what it will do is it will neutralize the acid. In terms of acidic oxide, CO2 is an acidic oxide, But then CO is what you call a neutral oxide. It has no reaction with the base at all, or it doesn't have any reaction with the acid at all. In this case, it will not get neutralized by the base because it will not react with the base. This remaining gas is dried and collected. This remaining gas is actually CO gas and not CO2. What is the volume of the CO? That is what they're asking. What is the volume of the CO gas there? Okay, we know that for a fact that only 0.50 gram of the carbon compound combines to form carbon monoxide. So carbon plus oxygen give you carbon monoxide. I have to balance my equation to do calculation. So I'm going to have half mole of O2 in front. And I know only 0.50 gram of that will go on to form the CO. So therefore, the mole of the CO is to the mole of the carbon is 1:1 from the balance equation. The volume of the CO is relative to the molar volume, which is 24 dm cube, 24.0 dm cube mole of gas according to your data booklet below the periodic table. 24.0 dm cube per mole of the gas at room temperature and pressure. So the volume of the gas in dm cube according to the answer and the options given here divided by dm cube per mole is going to tell you the mole of the CO gas that comes from these reacting masses. Only 0.50 gram of the carbon form the CO, so therefore the 0.50 divided by 12, that thing is mass over mR. This thing here is volume of gas divided by molar volume of gas. 1:1 on the other side is the mole ratio from the balance equation. Now I'm gonna get all of these now and rearrange the equations. So volume of CO divided by 24. Move up the 24 to the other side. What you're going to get is you're going to get multiply by 24. So I'm just going to do them in one step. And you just press your calculator. 0.50 divided by 12. Well, by right, it should be 12.0 from your periodic table. And then what do I get? I get multiplied by 24. I get 1, should be 1.0 dm cube to be appropriate number or significant figure based on the data that we have used. 2 or 3 significant figure would have been alright. So the best answer there must be option A there. Question number 4, oxygen difluoride has an oxidation number of -1 for the fluorine. And the reason of that is because fluorine is more electronegative than oxygen, and therefore fluorine will be delta negative, oxygen will be delta positive, and as a result of that, you can imagine that the fluorine will have a negative oxidation number. In this case, it's -1. The oxygen is -2 because you have OF2, so plus 2 as a result of it. I'm going to show you why. In OF2, you have the overall compound having 0 oxidation number. Oxygen is what you want to find. You have 1 of it. You have 2 fluorine. They already told you the fluorine will have a negative oxidation number. So the oxygen there is going to be +2. Your calculator doesn't show you the plus, but you know oxidation number. The plus and minus are very, very important there. So the oxygen is +2 there. In sulfur dioxide, our oxygen is -2. Our sulfur is +4. You can see the overall compound comes down to 0 oxidation number there. In SO3, we have oxygen -2 again. The overall compound is 0 oxidation number. So if you want, I can show you the math, but you should be able to do these oxidation number as part of your O-level, GCSE or IGCSE level chemistry. Now I have fluorine as an element, so there's fluorine 0 oxidation number. So there was fluorine -1 there. So fluorine -1 going to fluorine 0 is an increase in oxidation number. So this is oxidation. In terms of the oxygen is +2, the oxygen is -2 there. So the oxygen in OF2, +2 going to -2 is a reduction because there is a decrease in oxidation number. Reduce for the oxygen and oxidation for the fluorine. What do I get now? Which means the sulfur is also getting oxidized, +4 going to +6. So that leaves option B as the only possible correct answer. Question 5 looks like this is the ideal gas equation. You want the pressure in kilopascal. Just make sure you know that the unit given in the ideal gas equation, the pressure is in Pascal or Newton per meter square. The volume is in meter cube. The N there is the mole of the gas. The R there is the molar gas constant, joule per Kelvin per mole or joule per mole per Kelvin. The temperature must be in Kelvin there. My objective really is to try and find the pressure in Pascal, then I can convert it to kilopascal later on at the end for the final step. We are told that we have oxygen gas, so we know that in terms of the mole being mass of mR, because we are given the reacting mass, so we need to think about the mR. And to work out the mR, you need to know that it's a diatomic molecule, where you got two covalent bonds between the oxygen atoms as they want to get to a fully filled outer shell. So from your calculator as well as your periodic table, 16.0 times 2 give you 32.0. Now, rearranging this equation, PV equal to mass of mR, which is the mole RT. You want the pressure, so it's mRT over VMR like that. So the mass of the gas, 0.96, and then 8.31. And then the temperature there is, are we told about the temperature? 30 degrees Celsius. So you need to add 273 in order to convert degrees Celsius to Kelvin. So what I get is 303 Kelvin now. So times 303 Kelvin divided by the volume. So 7.0 times 10 to the minus 3 meter cube. And then the MR there is going to be 32.0. So sub that all into the calculator. 0.96 times 8.31 times 303 divided by 7.0 times 10 to the minus 3 divided by 32.0. What I get is 10,791 Pascal, as I mentioned earlier. This unit is in Pascal, and then I divide by 1,000. So divide by 1,000, divide by 10 to the 3, I get 10.8 kilopascal. If I just round it up to 3 significant figure, I look at the fourth one. So option C is the only correct answer there. Question 6, so we have this PCl5 dissociation into PCl3 and Cl2. We heat it up to 600 Kelvin in a sealed flask, so we have a closed system. A closed system is one of the first conditions for dynamic equilibrium. And we repeat the experiment with 1 mole of PCl5, and then we have a bigger volume. The only change here is bigger volume. So this is bigger volume of container. Everything else is the same. You still have 1 mole of the PCl5. You heat it to 600 Kelvin. When you have bigger volume of container, we know that PV equal to constant for an ideal gas, where we can assume here, obviously. Now the volume increases, means the pressure has to decrease. And we talk about pressure decrease that can affect the equilibrium positions depending on the moles of gases on the left and on the right. I have 1 mole of gas, so I have 1 gaseous mole of reactant. So on the left, I have 1 mole of gas. I have 2 moles of gases, so 1 mole of PCO3 there, and 1 mole of CO2, so 2 moles of gases on the right. So the greater the moles of gases, the greater is the number of molecules, and therefore they can collide more with the walls of container, and therefore they will exert greater pressure. So as a result of it, Le-Chatelier principle says, when I introduce a change to a system in equilibrium, the equilibrium will try to oppose the change. So when my pressure decreases, therefore the system or the equilibrium will try to increase pressure. When you try to increase pressure, you will shift to the side with greater molecules of gases. Therefore, it will shift to the right-hand side because the right-hand side has greater molecules of gases. Therefore, there is more collision with the walls, therefore greater pressure. This will counteract, this will oppose the change, which is lesser pressure as a result of the greater volume there. So when I shift to the right to increase pressure, therefore equilibrium shift to the right where I have greater number of molecules of gases. Ultimately, that will mean that I will have lesser PCl5 as the equilibrium shift to the right, and lesser PCl5, and remember bigger volume, lesser PCl5, you have concentration equal to amount, basically the mole over the volume. So you have lesser mole of these, but you have greater volume of the container, which will be the volume of the gas, as gas occupy the volume of the container. So definitely the PCl5 is going to have much lower equilibrium concentration, bigger volume, lesser mole, following this change in equilibrium position, following this change in the volume of container as a result of the pressure changing there. So B is the only option there. Question 7, this is about Hess cycle. So you have this conversion from glucose into ethanol and carbon dioxide. This is actually fermentation, but you're given the enthalpy change of combustion. So if I just put in the label, because labels are very important, you have enthalpy of combustion. For the glucose is minus 2820 kilojoule per mole. For the ethanol is minus 1368 kilojoule per mole. And we don't talk about the combustion of CO2 since we are not given that, because carbon dioxide does not combust any further. So does not combust any further. In fact, we know carbon dioxide is used to put out combustion, it's used to put out fire, right? So does not combust at all. So that is 0 there. Okay. Now in terms of the enthalpy change, if we are given the enthalpy change of combustion, it's the sum of the combustion of reactants. A lot of students just do reactor minus product, which is essentially a wrong concept. You have to think about what is your label. Is the combustion, the sum of the combustion of reactants minus the sum of the combustion of the product. Your reactant side, you have one molecule of that glucose, and then on your right hand side, you have two molecules. Therefore, I have to do 2 times the combustion, which is for 1 mole of the ethanol. So be very careful about stoichiometric quantity there. So minus 2820 minus bracket 2 times 1368 negative, and overall I get minus 84 sign value as well as unit. Always keep that good habit there. Number 8, which of these underlying substance is acting as a base? We know that a base is a proton acceptor. So proton acceptor is that. So here we can see the H2SO4 become HSO4. So the H2SO4 donates H+, and that is why you get this thing called conjugate base. Conjugate base is an AS level definition. It's the species you get after the acid donates the proton, and therefore it's acting as an acid there. Okay, as an acid there. Now what happened this next one? This is a negatively charged species. And what happened with the HCN? Well, look for the conjugate base. The conjugate base is Cn minus. The HCN donates the H plus, and that is still acting as an acid there. The HCO3 minus, what has happened there? Well, it has gone from there to there, from the HCO3 minus to CO2. So HCO3 minus going to CO2. What has happened? If you become CO2, you minus carbon, minus 2 oxygen, you have HO minus. So here it seems like it's giving away OH minus. Typically we say it's a H plus acceptor, but if HCO3 minus give away the OH minus, what does the OH minus do? The OH minus accept the protons, and that's why the OH minus accept the H plus from this acid. This is called HONO, which is basically HNO2. There are 2 oxygen there. This is called nitrous acid, and you will learn more about this in A2 benzene chemistry. Pretty sure the C is the answer, but let's just have a look at the last one. You have a carboxylic acid there, and what you get is this conjugate base. So conjugate base is the species that you get after the acid donates the protons. So here it's definitely acting as an acid. It loses the H plus, and you get this conjugate base. Acting as an acid there, D must be wrong for this underlying substance. So I was right about my hunch there. It gives away the OH minus, which can accept the H plus from nitrous acid, giving you H2 and CO2 there. Question 9, you have hemoglobin. If you do biology, you would know that hemoglobin has these 4 molecules of oxygen as a result of the heme group. Now this hemoglobin, 4 molecules of oxygen, this is equilibrium. And when this equilibrium concentration of O2 is this much, the equilibrium concentration of HP and that complex, so this is called a complex, it's got a metal center obviously, it's equal X and X. And you have 7.6 times 10 to the minus 6. So we know about Kc. Kc is going to be the complex concentration to the power of 1, and then the Hb concentration to the power of 1 because you have 1 in front of the balance equation, and then you have concentration of O2 to the power of 4. Now I'm going to put in the Kc value, which is, what's the value actually? We are not told about the value, that's fine. So Kc equal to the complex concentration, which is X, because we are told the concentration of these complex and these hemoglobin, they are equal at equilibrium. So X on top, X for the hemoglobin as well. I can see the X and the X will cancel, and then I get 7.6 times 10 to the minus 6 to the power of 4. X and X cancel, so I just get 1 over 7.6 times 10 to the minus 6. Don't forget to the power of 4 there. So press that onto your calculator, and then take the reciprocal. Reciprocal means 1 divided by, I get 2.997 times 10 to the 20. So this is mole per dm cube, this is mole per dm cube. They will cancel out, and therefore I will get 1 over mole per dm cube to the power of 4. So essentially they can ask you unit in a structured question. There will be mole minus 4 dm to the power plus 12. These are just simple indices. When you inverse it, you're going to get mole minus 4, and then the minus become the plus there. So this is closest to this value here, 3.0 times 10 to the 20. This is rounded up to 2 decimal place, or you can think about 2 significant figure as well. Number 10, we have a double bond between the 2 carbon atoms in an ethene molecule. Ethene is an alkene. If I draw alkenes, you can hopefully see that is a trigonal planar base there. And what you have is you have a carbon sp2, and that is why you have 1 p orbital which is unhybridized. And if you look at around one carbon, around each carbon, I have 3 bond pair. The 3 bond pairs are a result of 1 sigma, 2 sigma, and 3 sigma. So 3 bond pair there. And I've got 0 lone pair because I have used all my electrons for bonding. If I draw the display formula, you can see the carbon form 4 covalent bonds, 1, 2, 3, and 4, of which this double bond in the middle is actually 1 sigma and 1 pi. But the idea is carbon form 4 covalent bond there, 0 lone pair there. In terms of the shape, without any lone pair, the 3 bond pair repel equally, and this gives you a trigonal planar. So 3-sided and it's planar, and this is the very reason why you get 120-degree bond angles in this trigonal planar geometry. So trigonal planar 120-degree. In terms of hybridization, as I have shown you in my other lecture tutorials that you can watch at your perusal, you can just peruse through those tutorial playlists, topic by topic. So the number of bond pair plus the number of lone pair, 3 plus 0 give you 3 electron pairs, and for that you're going to get carbon and 1 of the 2s, and 1 plus how many give you 3, 1 plus 2 give you 3, carbon sp2 hybridization, which also means you use 2 out of the 3 2p orbitals for hybridization, and therefore you're left with 1 of these p orbital which is unhybridized on each carbon, and these unhybridized p orbitals, they can overlap sideways, and this gives you your pi bond. So the sideway overlapping in this case of the unhybridized p orbital give you the pi bond, and then your sigma bond there is between your hybridized orbitals, which is the result of carbon sp2 from this 3 bond pair and 0 lone pair there. So it's sp2 as well as sp2, so that will give you sigma bond there. Okay. Question 11. So we got to read the question very carefully. This is an endothermic reaction, meaning to say the enthalpy change is greater than 0. From the start, the reactant going to the product, from the start to the product, from the reactant to the product. So that is essentially your delta H greater than 0 for the forward reaction. Now they do want the forward reaction, reactant going to product. What is the activation energy? Activation energy is from the start to the top of the peak. So from the reactant to the top of the peak, one-headed arrow. I don't like the double-headed arrow, so B must be the answer there for the activation energy.